An E-rated fuse is indeed designed to melt within 10 minutes when subjected to a current between 220% and 264% of its rated amperage. The characteristic of an E-rated fuse, permitting it to carry 200% of its rated current indefinitely, is correct. Now let's address its applicability to the National Electrical Code, NEC, Article 450 concerning transformer protection. NEC Article 450 dictates that the overcurrent protection device, such as a fuse, be rated or set at a specific percentage of the transformer's rated current. The code aims to protect the transformer from overload conditions without causing nuisance tripping due to inrush currents or short-duration overloads. In the example provided, a 750 kV transformer with a 4160 volts delta primary connection has a full load amperage flaw. The calculation for the primary FLA of a three-phase transformer is as follows. The transformer's kilovolt amps rating is converted to volt amps by multiplying by 1000, so 750 kilovolt amps becomes 750,000 volt amps. Divide this value by the product of the voltage, 4160 volts, and the square root of 3, approximately 1.732. So, 750,000 divided by 4,160 times 1.732, which yields approximately 104 amps. NEC guidelines often permit the overcurrent protection device to be rated up to 250% of the transformer's FLA when using fuses for primary protection only. This allowance accounts for inrush currents that occur when a transformer is initially energized. Now calculate 250% of the transformer's full load amperage, 104 amps. This is calculated as 2.5 times 104 equaling 260 amps. The next standard fuse size above 260 amps should be selected, keeping in mind the available standard fuse sizes. Standard fuse sizes are typically available in increments such as 1, 3, 6, 10, 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, and so on. Therefore, a 300 amp fuse might seem like a suitable choice, as it is the next standard size above the calculated 260 amps. Now let's address the E-rated fuse. An E-rated fuse, such as a 300E fuse, does not necessarily have a 300 amp continuous current carrying capacity. The E designation signifies that the fuse meets specific time current characteristics, particularly its melting time at overload currents. For fuses rated 100E and above, they must melt within 10 minutes at 220% to 264% of their E rating, but the actual continuous current rating of the fuse may be lower than the number indicated in the E rating. A 300E fuse is not a 300 amp fuse in the traditional sense. The E rating refers to the fuse's performance under specific overload conditions, not its continuous current carrying capability. It's crucial to refer to the manufacturer's specifications to determine the actual continuous current rating and time current characteristic curves for the specific 300E fuse in question. If a 300E fuse could sustain 600 amps indefinitely, which it cannot, it would indeed present an issue, given that the transformer is only rated for 104 amps. The purpose of overcurrent protection is to protect the transformer from overloads and faults. Allowing a fuse with a significantly higher continuous current carrying capacity than the transformer's rating would defeat this purpose and could potentially damage the transformer. So, firstly, consult the fuse manufacturer's data sheets to determine the actual continuous current rating of the 300E fuse. This rating will likely be significantly lower than 300 amps. Secondly, ensure that the fuse rating is within the limit specified by NEC Article 450, which in this case is up to 250% of the transformer's full load amperage. Thirdly, select a fuse with an appropriate interrupting rating to safely clear any potential fault currents at the transformer's primary terminals. The interrupting rating is the maximum fault current that the fuse can safely interrupt without failing. In summary, the understanding of the E rating is correct, but its application to NEC Article 450 requires careful consideration of the fuse's actual continuous current rating, the transformer's full load amperage, and the applicable NEC guidelines. A 300E fuse is likely not suitable for protecting the 750 kV transformer in this scenario, as its continuous current rating is likely too low to meet the NEC requirements. To elaborate further, let's delve into the specifics of how to properly apply overcurrent protection for transformers, adhering to the guidelines outlined in NEC Article 450. Firstly, determine the transformer's primary and secondary voltages in kilovolt amps rating. This information is essential for calculating the transformer's full load amperage on both the primary and secondary sides. Secondly, calculate the transformer's full load amperage on the primary side using the formula mentioned earlier, the kilovolt amps rating multiplied by 1000, divided by the product of the voltage and the square root of 3 for three-phase systems. For single-phase transformers, omit the square root of 3. Thirdly, refer to NEC Table 450. 3 or 450. 3b, depending on whether the overcurrent protection is on the primary side only or on both the primary and secondary sides. These tables provide the maximum allowable overcurrent protection device ratings or settings as a percentage of the transformer's rated current. Fourthly, select the appropriate type of overcurrent protection device, such as a fuse or a circuit breaker. Fuses are commonly used for transformer protection due to their high interrupting ratings and relatively low cost. However, circuit breakers may be preferred in some applications for their reclosable functionality and ease of coordination. Fifthly, choose the overcurrent protection device rating based on the calculated percentages from NEC Table 450. 3 or 450. 3b. If the calculated value falls between standard overcurrent protection device sizes, select the next higher standard size, as permitted by the NEC. Sixthly, verify that the selected overcurrent protection device has an adequate interrupting rating to safely interrupt any potential fault currents at the transformer's terminals. The interrupting rating should be equal to or greater than the calculated fault current. Seventhly, coordinate the overcurrent protection devices on the primary and secondary sides of the transformer, if applicable. Coordination ensures that the overcurrent protection device closest to the fault will trip first, minimizing the extent of the outage. Eighthly, document all calculations, assumptions, and decisions made during the overcurrent protection selection process. This documentation will be valuable for future reference and for demonstrating compliance with the NEC. Ninthly, periodically inspect and test the overcurrent protection devices to ensure that they are functioning properly. This includes verifying the fuse ratings, testing the circuit breaker trip settings, and performing insulation resistance tests. Let's consider a more detailed example. Suppose a 1000 kV amps, 4160 volts delta to 480 volts Y transformer needs primary protection only. Firstly, calculate the primary full load amperage. 1000 kV amps multiplied by 1000 divided by 4160 volts times the square root of 3 equals approximately 139 amps. Secondly, refer to NEC Table 450. 3a. Assume that the transformer is not equipped with coordinated thermal overload protection. In this case, the maximum allowable primary overcurrent protection device rating is 250% of the full load amperage. Thirdly, calculate the maximum allowable primary overcurrent protection device rating. 250% of 139 amps equals 347.5 amps. Fourthly, select the next higher standard fuse size above 347.5 amps. In this case, a 350 amp fuse would be an appropriate choice. Fifthly, verify that the 350 amp fuse has an adequate interrupting rating to safely interrupt any potential fault currents at the transformer's primary terminals. Sixthly, coordinate the 350 amp fuse with any downstream overcurrent protection devices to ensure proper coordination. In addition to the above steps, it's also important to consider the following factors when selecting overcurrent protection for transformers. The transformer's impedance. The transformer's impedance affects the magnitude of the fault current that will flow during a fault condition. Higher impedance transformers will have lower fault currents, and vice versa. The available fault current at the transformer's primary terminals. This information is typically provided by the utility company or can be calculated using fault current study software. The ambient temperature. The ambient temperature can affect the current carrying capacity of overcurrent protection devices. Higher ambient temperatures will reduce the current carrying capacity, and vice versa. The altitude. The altitude can also affect the current carrying capacity of overcurrent protection devices. Higher altitudes will reduce the current carrying capacity, and vice versa. The presence of harmonics. Harmonics can cause overcurrent protection devices to operate prematurely. If harmonics are present, it may be necessary to use specially designed overcurrent protection devices that are immune to harmonics. In conclusion, selecting the appropriate overcurrent protection for transformers requires careful consideration of several factors, including the transformer's full load amperage, the NEC guidelines, the available fault current, and the ambient conditions. By following the steps outlined above, engineers and electricians can ensure that transformers are adequately protected from overloads and faults, minimizing the risk of damage and downtime. Finally, a 300E fuse is unlikely a 300 amp fuse. You must consult the manufacturer specifications.